Thank you very much for attending to this late afternoon session. Many of you have already attended this session for total control since noon with very interesting scientific and valuable studies and results. In this workshop, we would like to speak on certification issues. So how to bring wind farm control forward to the industry to allow the operators, the manufacturers to develop products all around wind farm control and find the acceptance for finances and stakeholders. I would like to start with a short introduction. Although we have many FarmConners and Total Controls members on board, here for those from external, a short introduction to the FarmConners project. It is an EU-funded research project in the Horizon 2020 framework, and its overall budget is 1.5 million euros. We are 12 partners, international, so European partners. And as I said, the workshop aims to answer the question how certification could bring wind farm control commercially forward. Those are our partners. DTU is the head and coordinator of this project, and then we have TU Munich, Catholic University Leuven, SINTEF, TU Delft, ForWind from Oldenburg, Vestas, DNV GL, ENGIE, which is now merged back to RWE, Catapult, Sener from Spain, and ENGIE from France. And we also have an advisory committee with Siemens Gamesa on board, NREL from the US, TNO from Holland, Carbon Trust, and Naturgy. So we have a quite representative members in the wind industry here within this project. And just to show you the packages, the work packages this project is divided into. So we have work package 1, testing and validation. So those are the benchmark cases running right now. The work package 2, which is led by DNV GL, and which is here this workshop about certification and standardization. And finally, work package 3, the European electricity market and how to integrate wind farm control as a measure to commercialize wind energy into a levelised electric market. Yeah, in work package 2, we have 3 deliverables. We have already published 1 paper in summer this year. It is available on the website on wind farm control, windfarmcontrol.info. It's a position paper on the state of the art, and my colleague John Nwobu will report more on this after a minute. The second deliverable is exactly this workshop. So after this workshop, we could make another green hook on this work package, and we will issue a final report in the middle or at beginning of next year. It's not clear when exactly, but we would like to give recommendations for certification on wind farm control in more detail, bringing in all the experience gained in this project from all those research and interviews. Yes, this is our fully packed presentation guideline for today. We have the summary of the position paper, which I just mentioned, given by John Nwobu from RE Catapult. Ervin Bossany will report on turbine loading and wind farm control. Nikolai Hille, colleague of mine, will report on the certifications report we have identified so far. There are not many, I can say in advance, and also the perspectives of OEMs and operators with regard of certification of wind farm control on their existing projects. Then Vlaho Petrovic will report about power control, active power control strategies and how they might reduce the loading of wind turbines, which of course for us as a certification body is a very important issue. How could be maybe the lifetime extended by those intelligent strategies? And last but not least, Benoit Bichet from ENGIE will report their experience on wind farm control implementation in their existing wind farms in France. All right. So now I would like to hand over to John Nwobu from our RE Catapult. Gregor, you can kick me out so that John has the opportunity to load up his presentation.
Thank you, Andreas. I'll just try share my screen.
I think it's easiest if you just stop your sharing.
Okay.
So
1 second. All right. Yes.
I found it.
Okay,
Thank you.
Try mine now. Let's see if that works. Okay. Just checking if everyone can see my presentation.
Perfect.
Yes, lovely.
Okay. So thank you, Andreas. My name is John Nwobu. I'm a researcher here at the Option Renewable Energy Catapult. Part of the team working with Andreas and the rest of the partners in this deliverable 2.0 position paper. Just presenting on behalf of the work done, which was we're the technical lead in that as well. Also done with another colleague of mine who is not here today, Andreas Manjock as well. And I'll just be giving an overview of what the position paper is and in terms of the actual contents in there as well, just to give everybody a kind of feel of what we did and kind of the challenges we saw and some of the propositions we put forward while looking at this as well. So the slide is the overview of the table of contents in it. So, and these are the different chapters in it. So we have a chapter on regulatory landscape, where we looked at the different certification schemes that are available at the moment and standards as well. Wind farm control functionalities, where we look at the state of our where wind farm control is at the moment, novel strategies, and things around how you could integrate the wind farm control into the existing platforms as well, on the wind farms as well. We looked at another aspect of wind farm control economics, looking at the different market structures, the economic potential of wind farm control, and also how that could also foster the use of providing ancillary services as well. Challenges as well, turbulence and wake effects, grid requirements, wind turbine components as well, in terms of that, and proposed solutions as well, which Nikolai later on will be covering some of the proposed solutions we saw, which could probably aid making certification a bit easier as we move forward as well with farm control. So starting off with the regulatory landscape, this is just a summary of the key outputs. Basically, what we're trying to do here, just let me put on my video as well so everyone can see me. What we're trying to do here as well is, trying to keep the loading effects to be within the defined component design limits as well with the wind turbines. And in this case, there are two kind of certificates that can be issued in regards to this as well. The rotor NASA assembly 1 RNA and the project certificate for site-specific support structures of wind farms as well. In terms of certification schemes, what we found out was there are 2 certification schemes for wind farm control. Both are the IECRE standards listed here as well. As much as they are there and there's a mention of wind farm control, what was noted is that there was no clear guidance about how these should be performed in this documents as well. And that's just a diagram that summarizes what that is in terms of the certification scheme in the document as well. Another aspect is the DNV GL service document, which in the more updated version coming out to be published in 2020, wind farm control is to be considered as well in the site-specific design assessment, SSDA. And that's the diagram on the right, which shows what that is. And in this case, this covers includes a minimal analysis or review of the following listed bullet points down there as well, such as the wind conditions of the sites, the wind farm influence, site complexity analysis, and site-specific extreme loads as well. Finally, what we did was to look at the standards as well that are available at the moment. The list of the standards are there in the position paper document on the website if you want to have a full list, but the snapshot here is an extract from that document as well. Summary from here was the existing standards in practice do not cover wind farm control explicitly, and there still needs to be a lot more to be done in terms of getting those standards up to date as well. And in the later slides, there were some recommendations put forward from a project here, FarmConners as well, which could help to guide this forward going on as well. The other aspect with farm control functionalities, which was more about the different novel approaches, which are of control approaches which are being used at the moment. And there was a review on some of them. These are just the two listed ones out of the document: axial induction and wake steering. Axial induction, which has to do with modification of the energy harvests of either upstream or downstream turbines, so that the wake interaction effects can be mitigated. And in this case, challenges which we see there is that although this is seen as one of the techniques that could actually foster wind farm control, in terms of wind tunnel tests and field tests, it still calls it into question on how this might actually be used for wind farm power increase as well. For wake steering, which is when you're trying to move the yaw alignments, which is one of the more promising techniques there, and steer the wakes in terms of to modify how the turbines react, downstream turbines react, and reduces the wake interactions in the wind farm. That's seen as a promising technique, and which has also been tested in real wind farms as well. There's some other ones mentioned in the document, which everyone is open to have a look through as well. And so we did a review on that. We also looked into aspects that has to do with the integration into the existing wind power plant kind of control of wind farms. And what was proposed here was the hierarchical design requirements kind of way of doing this, where there's a 3-level hierarchy, lowest level based on optimizing the energy harvest from the wind farm, and the more very high level focus would be the safety and structural integrity of the wind farm as well. So in here, I think one of the things we'll discuss that there needs to be some sort of trade-offs between the several design goals, which needs to be found at those different levels as well. And list of bullet points here explains a bit of those as well, such as load reduction against maximized energy yield, and certification issues mainly addresses aspect of safety, structural and electrical integrity of the wind farm as well. Wind farm economics was another aspect looked into in this position paper. And in here, we reviewed the different electricity markets. And summary here was that for wind farm control to participate in electricity markets, this would depend on having a very robust algorithms or control systems that can do that, and that can control the control actions. Also adhere to the different market participation rules, and also importantly abide under the grid codes for the normal operation of the wind turbine. Two recent developments were noted in this report. One was the power available scheme, which is where the wind farms are allowed to provide headroom capacity, and that's sent over to the TSOs in their operation control rooms, and they have an idea of what that headroom is, and you're able to participate based on that in markets such as balancing mechanisms. Also, yes, auction trials, which opens up the wind industry into different markets such as the day ahead and intraday markets as well. On another aspect which was summarized there was the economic potential for wind farm control. And this was gotten from a review of the CL WindCon project, where there was a feasibility study for the analysis of wind farm control in there. And this slide summarizes some of the outputs from that study. So what was seen there is that wake steering, which was the actual control approach used in this study, was actually economically viable when it looked at in the aspects of the apex electricity spot markets and prices. Also, that slightly improved the availability of wind farm and also increased the annual energy production from the wind farm as well. What you could see on one of the tables on the right-hand side is that although there was an increase in the lifetime costs, the net gains from the energy sales actually offset that, and you have net differences of about 1.1% of the whole project cost as well, which actually shows significant promises for having your control used in the wind farm as well. And lastly, in aspects of the levelized cost of energy as well, that was shown to slightly improve that as well, by from 31 euros or to about 31.35 euros as well, or 35 euros as well. And also challenges for the wind farm commercialization. This was mostly around understanding what the effect would be with turbulence and wake effects in terms of the challenges, and going into the different models used in terms of how this is done. And the one discussed here was the present turbulence model, which was reviewed and shown not to be detailed enough to cover the complexity of the wave physics. And also the IAC standards as well was also addressed to understand the different methods of how it's done. For example, verification is done on a single turbine. And for large offshore wind farms, this common practice which was to separate this into clusters to perform the different load analysis of the representative turbines for each cluster as well. I think the findings from this, however, these approaches, these are still not suitable and for use in terms of understanding the variable farm control strategies which are to come into picture, which where people are looking into at the moment as well. Also, yeah, it was just about moving on from that model to the dynamic wake meandering model, which actually is an alternative method of doing that and captures a bit more the key features, and that's while being also be a bit more sufficient than the initial French-Dem models. There's still significant challenges, which in terms of how you can actually use this to calculate the different wake effects in all the different positions as well, wind farm and the effect on the wind farm controller. Also, there was the mention of the different simulation tools which are already available to do this kind of modeling analysis as well. But there's still a significant challenge in terms of understanding how you could, more or less progress this to perform full wind farm simulations as well, including wind farm control activities. Finally, here in challenges was the risks for the wind turbine components. And here was a list of recommendations, which was to develop the criteria requirements for certifications, that's to be a bit further terms of the standards. Listed here are 3, which listed here, but there's a full list of the recommendations in the report as well, which could go ahead and have a look in detail if you want to do that at a later point. And finally, is just proposed solutions. And yeah, I think Nikolai will be going ahead in a couple of minutes to give a bit more detail into the first 2, which was the temporary and conditional product certification. And this is an approach which extends the conventional site-specific design assessments to include additional inputs for wind farm control strategies, and also the approach of how you can use risk-based certification carried out to issue certificates, to help assess the safety concerns that might be with the wind turbines and the wind farm. Finally, is proposal was also to see how we can start to use regulatory sandbox approaches, which are ways where you could implement new novel strategies, and with the exception from the obligation to comply within the existing regulations, such as grid codes, and gives a more or less a safe room to do trial studies with this kind of wind farm control techniques when developing as well. And that's summary of what we had for the D 2.1 position paper. And thank you everyone for listening as well. Okay, back to you, Andreas.
Yes, thank you, John. Yeah, are there questions from the audience? I haven't seen so far any comments in the chat. So maybe then I can add to those information from John, that it is the fact that still the standards in the wind industry, the IEC or the DNV GL standards, only have mentioned wind farm control, and there are no clear procedures yet. And we are thinking on bringing in the results from this research work in updates of our guidelines to make also to give guidelines for certification of wind farm controls on the changes. It is a change in control. Control will always change loads, and therefore there will be probably some publication next year's from our side and maybe also from the IEC side. Yes. Then if there are no further questions, Gregor, do you have received any? I have a question from Gunnar. Maybe Gunnar, would you open your microphone and ask your question?
Yeah, well, I could do that. I was a little bit late in the presentation, so it might be that I missed something. But my question is simply, did you, besides active wake control using your turbine, also consider derating of turbines in the study in TLWincon?
Yes, of course. And the challenging thing is to balance somehow the benefits and the disadvantage for the individual turbine on the damage equivalent load level from those strategies. We have both situations, that we have savings of damage equivalent loads that has been shown, for example, in the total control presentation by Arnaud just an hour ago. But we also have this wake steering with high yaw angles, which on certain positions might increase loads. And so it has to be identified how much benefits I got and how much investment I have to put into structural strengths. But both has been considered, both strategies.
Super, thanks. We're also working with those concepts in total control.
Yes.
So maybe we can enlighten this topic further going forward.
Of course, and my colleague Nikolai, who will be next, maybe also can build the bridge to total control here as project manager involved in total control. Okay. Good then. Then Nikolai, maybe.
Yeah, is it me or is it Ervin before?
Oh, I'm sorry. You are all right. So I was a quick tour ahead, a jump ahead. Ervin, are you in the line?
Yes, I'm here and ready. Yeah.
Okay, fine. Then I remove my sharing.
Yeah.
Oops. It's now I have, and you can start with your presentation.
Oh, it's telling me you've started sharing.
Okay. Yeah, you're right.
Right.
Sorry.
Okay. Now I can share. Thanks. Okay. Can everybody see that and hear me?
Yes, maybe you could speak a little bit more louder or speak up a bit.
Yeah, I'll come a bit closer to the microphone. Is that okay?
Great. And your presentation is online.
Okay, good. So this is about turbine loading in wind farm control. Requirements and modeling approach. Did I write that? Yeah. Okay. And the next slide, yes. Well, I don't need to spend time on this one. This is just showing the difference between steering and induction control and the need to find optimum set points for turbines in the wind farm. And how do we define the optimum? Because it depends on energy and loading. That's another old slide. Modeling requirements for this. So we are concentrating on the engineering models here, which are fast, but in some senses low fidelity models. We need to have a detailed representation of the turbine wakes in different atmospheric conditions. We need to be able to realistic time varying wind conditions, accurate modeling of turbine control dynamics, and we also need time domain simulations long enough to capture the low frequency variations in wind conditions, hours or days or longer. But we need to have a short enough time step for the simulations to be able to capture the main turbine wind farm control dynamics, which are important for this. So something like a 1 second time step or something of that order. And this has to be fast enough to do many repeat simulations for design iterations. So that's why we choose the engineering model approach for this rather than high fidelity flow models like large eddy simulations, which are just too computer intensive. So we have a time domain simulation model called LongSim, developed at DNV GL. This contains a choice of different engineering wake models, which are simply embedded in a stochastic wind field, as you can see in the simulation there. We've got a choice of different models available. For example, for the Gaussian wake profiles from either Ainsley or the Stankart models, different options for wake turbulence, different options for wake superposition, lateral deflection due to yawing, so on. In models, wake meandering and advection, the turbine details, including the supervisory control. So, for example, in this simulation, you can see the yaw system dynamics going on. This is a wake steering simulation. And the wind farm control algorithm, so that needs to be able to estimate wind conditions from turbine signals. It needs to be able to look up set points and implement the set points in some realistic way in the time domain. This is actually a simulation of a row of turbines at Sedini Wind Farm, which we used in the CL WindCon project. The wind field is generated from historical site data, in this case from a Met mast, and that then gives you conditions at one point, but we can generate from that a whole wind field, which is representative of the site. And then we use this to test and tune the algorithm details. We can test it against different wake models, and we can evaluate the power increase of the operational parameters like the amount of yaw duty and so on. This shows the design process. So we've got the long sim model here, which is capable, first of all, of doing steady state set point optimizations, where we look at all sorts of different wind conditions and calculate the optimum set points for the different turbines in each wind condition and generate a big lookup table of set points. We adjust those for robustness to account for uncertainties in wind conditions, because you never know what the wind condition is precisely, and actually it varies across the wind farm. It's never the same everywhere anyway. We then build that into a dynamic wind farm control algorithm, which has the task of determining the wind conditions from whatever measurements happen to be available, and then using this robust lookup table to generate set points, which are then manipulated in an appropriate way before sending to the different turbines in the wind farm. And then LongSim does the dynamic simulations using a realistic wind field made from site wind data to evaluate the performance in time domain of this control algorithm, and we can iterate around the loop here to adjust the dynamic parameters of the controller. And the simulations will give us the performance, the energy production, yaw system duty, and loads, and so on as well. And then nice thing is that we can run a test on site. We can use SCADA data from during the tests to generate a wind field, which allows us to model the behavior of the wind farm to mimic what it was actually doing during the tests, and we can compare the simulation results against the SCADA data. And that's a very useful diagnostic tool, as we discovered in the Sedini tests, which are here. In the CL WindCon project, we were doing actually some induction control tests on this row of turbines in green here. So we did that design process. We developed a toggle test where we switched the control on this row of turbines on and off at regular intervals. So we could compare the behavior with and without, and we did some companion simulations. And this is just a result showing the power in different wind speed bins with and without the control, showing a small increase there. This is points per bin. And these are the companion simulations where the actual SCADA data is compared against the LongSim predictions using the wind field generated from SCADA data. This is power at a turbine. This is the set points at a turbine showing toggling on and off. So that was very useful. So what about the loads? Loads obviously very important. Site-specific load calculations, you'd ideally look at every turbine in the wind farm, in every wind condition, every wind direction. If you use aeroelastic tools, that can be quite prohibitive. So wind farm control changes the loads. So the turbines whose set points are being changed, you'll see different loading. So for axial induction control, you get rotor speed and pitch angle changes, which will generally reduce thrust or mostly reduce the loads on that turbine. Large yaw misalignments if you're doing wake steering, which will make some of the loads higher and some of them lower. So it has a mixed effect on the loads. And then if you look at the turbines who are wake affected, they will see increased wake velocities, which increases some mean loads, but generally fatigue loads will reduce due to reduced wake turbulence. There will be changes in partial wake immersion, which affect the rotor, the asymmetric rotor loads, and different loads will be affected in different ways. So it's a very complicated picture. And of course, the extent to which each turbine is either controlled or wake affected or both changes with the wind direction. So the annual or lifetime effects on loads, it's a very complicated picture. So how do we model these loads? Well, to use a fatigue loads database. This consists of many thousands of 10-minute dynamic aeroelastic simulations for which we would use bladed, but there are other tools, and covering a multi-dimensional hypercube of different conditions, so different wind speeds, turbulence intensities, wind shears, yaw misalignments for wake steering, or delta set points for thrust reduction in axial induction control. We can model the single wake effects in bladed, but the database, if we wanted to do yaw misalignments properly, wake effects properly, we would have 3 or 4 more dimensions for different centerline velocity deficits, different wake widths and centerline offsets, and it still wouldn't account for wake meandering and propagation dynamics and crucially multiple wake superposition effects. At the moment, the only way we have is to change the turbulence intensity if you're in the wake, and that's clearly not an adequate representation. So I'm going to talk about a new approach where we're doing short targeted simulations to identify deterministic load contributions from wind shear, yaw, partial wake, immersion, gravity, and so on. And then we fit simple empirical models to these results. Then we do a small number of stochastic simulations with turbulence to identify transfer functions which embody the effects of turbulence and structural dynamics on the different loads. And then we can combine all these different load contributions together, the deterministic and stochastic contributions in the time domain, to get the total loading. And that requires a leap of faith that we can actually combine these loads, but it does actually seem to work quite well. And in that way, we can deal with multiple wakes and so on in a consistent way. So to illustrate this, so we separately model the deterministic effects of wind shear, yaw, partial wake, and so on each load. We identify the effect in terms of the 3P Fourier harmonics, which are generated, also the 0P or mean levels where appropriate. And we could easily extend this to 6P and other harmonics if necessary, but these are pretty small effects. And then we fit simple functions to predict the amplitude and phase of each of these Fourier harmonics as a function of whatever the driving effects are. So here, for example, we see the amplitude of the 3P component of a tower MX, tower base MX load as a function of the shear, wind shear exponent. And you can see some actual points, simulated points with bladed and the fitted model, which is the red line. Here we have yaw misalignments, and in this case I've chosen tower base MY moment, and this is the 3P contribution as a function of yaw misalignment. Here we have the 3P thrust contribution and the effect load on the hub, as a function of a parameter which actually combines different wake parameters, different partial wake immersion parameters, so wake deficit, wake width, center line displacement, this sort of thing. So there's not a nice simple line you can plot through these results because they're all different effects, but you can see the difference between actual and predicted. So those are the deterministic effects, and for the stochastic effects, we calculate these transfer functions from wind speed to each of the loads with no deterministic effects, and they're just purely the turbulence and the structural vibrations. And we repeat for each wind speed and for each axial induction set point. Now these transfer functions are largely independent of turbulence, which is very useful. So here we see that the transfer function to stationary hub MZ, that's the yawing moment, from wind speed to yawing moment for two different turbulence intensities, 10 and 20%, and it's almost identical transfer function, so it's very useful. This shows the filtering of the transfer functions to make them smoother and get rid of the noise. And then we combine the stochastic and deterministic components, and we can actually compare this to bladed simulations, where we can run a bladed simulation which is simple enough to, or for a situation which is simple enough for bladed to be able to cope with. So no multiple wake effects. But we can have a situation where we have wind shear, and we have partial wake immersion here, and a yaw misalignment as well. So that's already quite a complex situation which bladed can model. And on the right here, we've compared the predictions in red for the new model against bladed simulations for these conditions, for this particular condition, using two different turbulence seeds in bladed, because turbulence seeds make quite a difference. And you can see the time domain loading here. This is the blade root bending moment I've chosen. This is the spectrum, showing you get a very good match to the spectrum of the load. And down here we have the damage equivalent loads for different Wöhler exponents for this particular load. So again, very good prediction. So that's very reassuring. And so we say we can extend this now to model situations which bladed can't deal with, such as multiple wake immersion, wake superposition, and so on. This is just a little study using the model and also using bladed, because it's something you can do with bladed, which is just the effect of yaw misalignment on the loads. This is a board for wake steering. I've illustrated here the nodding moment. And this is the mean effect here. So with a negative yaw angle, we get an increase in mean nodding moment. For positive yaw angle, we get a decrease. And this shows a couple of bladed seeds in the long sim prediction using this model. And they're telling the same story, not identical. Here is the damage equivalent load on the same load, the nodding moment, damage equivalent load. And in this case, the green and purple are the bladed simulations with two different seeds. So a lot of seed variation there. And the new model is giving a very similar result, which is well within the range of the different seeds. So it's showing the same story, which is that the highest load is at 0 yaw, and then there's a bigger reduction at positive yaw than negative yaw. This is blade root moment now. Again, against yawing angle, and showing similar sort of things, so bladed and long sim comparisons for the mean blade root movement, and here the damage equivalent load, showing again a reduction for positive yaw and an increase for negative yaw, and a good agreement between the models. A few slides just on the total control project now, where we've seen this Lillgrund wind farm already. 48 turbines closely spaced. We've done some set point optimization and dynamic simulations using wake steering and induction control. We're currently designing a field test of induction control for this wind farm. We've been optimizing set points just for power, ignoring loads, because we won't be able to measure all the loads on the wind farm. But then we've repeated some simulations, optimizing also loads, and this is an illustration of that. So the first optimization is power only, and the second optimization is for power and loads. And here, just as an arbitrary choice, just to illustrate, I've put a 90% weighting on the total wind farm power and a 5% weighting on the maximum blade root damage equivalent load, Euler exponent 10, the maximum value on any turbine in the wind farm. I'll put a 5% weight on that. It's just for illustration, the sort of thing you can do. The tower base NY, I've used the sum of the MY over all the turbines, and again, the 5% weight. That's pretty arbitrary merit function, but we can choose whatever we like. We could also use the difference in loading across the wind farm between the turbines to try and even up the loading across the wind farm. So power only optimization gave a 1.7% increase in power, a large decrease in blade root fatigue, 35%, and a significant increase in decrease in tower base fatigue. So although it's a power only optimization, the loads are coming down very nicely across the wind farm. This is the optimization for power and loads with this very arbitrary choice of weightings. And the blade root fatigue has come down some more because we put a weighting on it. But that's at the cost of not achieving quite as much power increase and also not as much tower base fatigue. So, but actually what this one tells us is we don't really need to put weightings on these loadings because we're already getting very significant load reductions. Finally, this is some time domain simulation with these loads. So simulating the loads as well. So I'm simulating the entire wind farm. I'm simulating the loads on all the turbines in the wind farm. And I've just picked out 3 turbines here for illustration. So the black one is upwind, and the green one is very wake effective. The red one's in the middle. The top simulation is the base case with no control, and the bottom simulation is with the axial induction control active. And this is the axial induction control just optimized for power. But you can see that the loads have come down quite a bit. This is the summary here. So for the upstream turbine, the black one, the mean load, this is the tower base, no, the blade root bending moment, sorry, that I'm illustrating here. It's a 3-hour simulation. The mean load has come down, the standard deviation has come down. I could also calculate damage equivalent loads here. I haven't done that here. I ran out of time. Turbine 4, the mean and the standard deviation have both come down. The green turbine here right at the end, very heavily wake affected. The standard deviation is still coming down a bit. The mean has actually gone up slightly. The fatigue would have come down if I calculated the damage equivalent load. So it's just an illustration. You can get all these loads on all these turbines using a simulation which is almost as fast as if we weren't calculating the loads at all, because we're not simulating the turbine structural dynamics. We can use a time step of 1 to 5 to 10 seconds and still get these loads at very high time resolution for the model. So conclusions, this surrogate loads model accounts for wake effects in detail, gives good agreement with bladed when you can compare directly with bladed, allows loads on all the turbines in the farm to be evaluated much quicker than with aeroelastic simulation. We use a relatively small number of training simulations compared to the standard database approach, and they're shorter simulations, many of them, because they're just constant wind simulations to get the deterministic effects, and relatively few turbulent simulations for the stochastic effects. We can do the set point optimization, including the loads, and then we can do these time domain simulations, also including the loads. So that's, I think, going to be pretty useful. These are the 3 projects that I've referred to. This is obviously FarmConners, but there's a lot of work that's gone on in CO-WinCon and total control. And any questions?
Hi, Ervin. I have a single question.
Hi.
Thank you for your nice presentation. So when you do the optimization, including both loads and power production in the objective function, how do you then balance the loads and power production in this metric?
Yeah, so what we do is apply weightings to the different terms in the cost function. So we can apply different weightings. There's always a big weighting on the power production, because whatever you do, you certainly don't want to lose power production, and probably you want to increase it. But then for the different loads, we can generate different loading terms and give them each weightings depending on how important we think they are. So actually in the example I gave, I had a weighting on the blade root bending moment and a weighting on the tower base moment. But even that you can do in different ways. So I chose to use the maximum of any turbine's blade root bending moment. And I chose the sum of all the tower base bending moments. But you could also use the variation between turbines of different loads, the different bending moments or whatever. And you can give them weightings depending on how important they are. And it's actually very difficult to put an economic weighting on these loads. It depends on what effect you're having on the operation and maintenance costs. If you reduce the tower base moment, or if you reduce the blade root load or the nodding moment, or this is all going to have different effects on different components, and on the operation and maintenance cost, and on the lifetime loading. And one way you can do it is by looking at lifetime loading effects and how much lifetime extension you might get as a result of doing this control. And that will mean that you're generating power over a longer period, which will give you an economic benefit, which is quite straightforward to quantify then, because it's just the extra power generated over more years. So that's one way to do it.
And that's, of course, the crucial point. But what I wondered a little bit about was that for the example you showed, it almost seems that the power production metric outperformed the load and power production metric also on loads.
Yes, that's right. So that example, which let's just get back to that one, was, as I said, it was this one. Yeah, it was a very arbitrary choice of cost function, just to have something to illustrate, to be able to quickly produce some results for this presentation. But what's happening here is it's obviously very difficult to further reduce the blade root bending moment. So I've put in this loading, and it has managed to squeeze in a bit more reduction, but only at the cost of the other terms in the cost function doing less well. So what I would say is I shouldn't have this weighting on the blade root bending moment, because we've already got a massive reduction in blade root bending moment. So there's no point in trying to do even more. So if I did this again, I would choose a different, some different metrics here. The tower base, even the tower base is already quite massively reduced, so that's very nice. I could try and reduce that some more, but I certainly don't want to squeeze more out of the blade root bending moments. So we can play around with these weightings. These are just two that are shown for examples, but probably more relevant might be the variation between turbines across the wind farm in, for example, tower base fatigue or whatever. And actually the next job I'm doing for total control is to do exactly that. So I'm looking at when the wind farm is curtailed, so that you're reducing total wind farm power. How do you do that to have the best effect on loads? And I'm going to use this same scheme to do that. So I can look at, for example, the variation in tower base fatigue and try to even that up across the wind farm as much as possible for a given power reduction. Does that begin to answer the question at least a little bit?
Yeah, that's a perfect start of this discussion that I'm sure will go on.
Yes, Ervin, thank you very much for this very excellent presentation and this exciting results on long sim. And I was really surprised to see the good agreement of long sim fatigue damages on certain points simply, but with Bladed, which has a full BEM aerodynamic model with everything in it. It seems that long sim is able to predict the loading based on this big database for a full wind farm. And then it would be possible to identify maybe the most loaded turbine within this full wind farm, isn't it?
Yes, absolutely. So on the next slide here, if I look at the results of these simulations, I would be able to, I've just picked out 3 of the turbines here, but I could very quickly calculate the damage equivalent loads for all those turbines from the time history loads that I've generated there. So that would be a very quick step. And
do you think it would be possible then to have a site-specific certification, maybe, if there is an operator saying, I would like to know which lifetime or which damage I have on minimum lifetime, which turbine would be the most loaded turbine, to do this within a certification procedure?
Yes, I think you could. So you would have to define, obviously, the windrows.
Yes.
To define a set of conditions to look at. And for each of those conditions, you could run a simulation. I mean, you can do it in steady state also in long sim, which is even quicker because then you don't have to run the time domain simulation. But the time domain simulation will be more precise, but then you're relying on doing particular simulations, so you might want to run different seeds like you do with Bladed for single turbines, this sort of thing. But yeah, absolutely, this could be used.
Sounds promising. I see that there is another question from Stefano. Maybe Stefano, would you like to raise up your question?
Yes, here I am. Can you hear me?
Yes, good.
Okay, so thank you, Ervin, for the presentation. And Cacciola Stefano from Politecnico Milano. I expect also wind farm control would impact also ultimate loads. And here the point is it possible for you to create some surrogate model also for estimating the impact of wind farm control in terms of ultimate loads, which are, of course, driving loads for design of wind turbines?
Yes, that's a very good question. Yeah, possibly. The problem with ultimate loads, of course, is that they're very specific to particular cases. I suppose for the turbulent ultimate loads, so the normal operation ultimate loads where you don't have turbine failures or strange gusts, that's if you're using turbulence and extrapolating to the extreme loads, then you could relatively straightforwardly extend this approach to those loads. Those aren't necessarily the final ultimate loads, of course, because the ultimate loads depend on which of these many different sorts of load cases and failure cases and everything else happens to pop up the worst load. So I think in a wind farm context, you know, if the highest load is due to some fault case, and that fault case is in a turbine which is in a different environment because it's in the middle of a wind farm, you could end up having to consider quite a lot of cases. It would need quite a lot of thought, I think. But it's
so we have something to think about.
Yeah, something definitely to think about.
Okay, thank you so much, Ervin.
Yeah, indeed, it was a very good remark. And of course, this is what we would, as a certification body, would look for. Could there be any negative impact if an extreme gust passes the wind farm, which is operating on wind farm control? Could it have a negative impact or not? Very, very interesting. All right. I think there are no more questions in the chat. Then I would like to turn over now to Nikolai. Nikolai, I see you.
Yes.
Thank you very much, Ervin. So, Nikolai, you are able now to share your presentation.
Can you see it?
Yes.
One moment, please. Well, anyway, works out. Yeah, thank you, Ervin. Thank you, Andreas, for handing over to my topic here on certification and the work we are doing or will do. There's a lot of tasks to think about, and yeah, but also some answers on the way. So what I will talk about is today some introductory words on certification. Then describe 3 proposals for wind farm certification approaches, DNV GL we have already today, and then report on interviews we had with wind turbine OEMs and operators, and yeah, regarding wind farm control. So what is important to me for certification is that we have, in fact, 2 certification streams for wind farm control to consider. So the first one is on the wind turbine structural design, which are all aware of the type certification on wind turbine level, and then wind farm related site-specific design assessment or project certificate. And we have a second and separate stream that is about grid code compliance to be considered. And there also certification on wind turbine level can be performed, and also a project certificate can be achieved on wind farm level. I would focus today only on the wind turbine structure certification stream, and there we'll have to consider wind farms that might be retrofitted with wind farm control functionalities, and wind farms which will be newly designed to apply wind farm control. In FarmConners and Total Control, we are working on detailed requirements for wind farm certification, but the processes for certification are in place already today. So let's have a look at these approaches available. So the first approach I like to call straightforward integration, where we expect for the first wind farms to apply wind farm control features will be retrofitted wind farms, where the impact of the technical changes with wind farm control features will be less complex. And so the integration into the existing wind turbines and the existing certification will be rather easy and allow a straightforward certification. One example could be a rather simple example where an induction control might be implemented for one row, the first row in an existing wind farm. And there will be a rather simple argumentation that the loads will be not higher than the previous existing design envelope proposed. So the inclusion of the certification will be rather easy. The second approach would be a risk-based certification. So for the situation now where we still have limited guidance for wind farm control in existing standards, we might miss clearer details how to proceed for certification for more complex wind farm control designs. And there we can offer an approach named technology qualification, where we together with the wind turbine OEM would dive into the technologies applied and identify risks for that approach. And together we would also identify how these risks can be mitigated. And one example would be to perform a measurement project on a wind farm, an existing wind farm, to see how the performance of this approach is. This could be a whole wind farm, or as on the right-hand side shown, there's a picture of the hardware in the loop test stand. Our colleagues from Renewables Advisory have set up in the front. There's a wind farm controller, and in the back you can see the hardware in the loop testing environment. And this technology qualification approach will provide a clear path, so to say, a cooking recipe, how to reach the desired certification, like site-specific design assessment. And if this recipe is followed, we'll have in the end the same comparable safety level as with a type or project certificate. And the third approach is called here certification facilitated by measurements. In our new service specification for project certification, we have a new section named wind farm control, where we propose for the application of simulation models or tools, as we heard about in the last presentations, an approach where validation has not been yet performed to the level that would be necessary, or for certification to ensure good enough safety in this aspect. And there we would propose the approach that the load simulations by the wind turbine OEM would be performed using these tools and wake models anyway, while the assessment will be done on a plausibility checks only on a little bit lower level, but we will issue a conditioned site-specific design assessment, including this wind farm control, which will have a limited validity. And during this period, measurement project will be set up to accompany the wind farm with measurements during the first year of operation. And then the results of these measurements will be compared with the initial assumptions from simulation. And if the assumptions can be confirmed, then we can issue an unconditioned site-specific design assessment with the intended configuration. If there are still deviations, it might be necessary to mitigate the deviations, for example, by modifying the control to some extent, or changing the expected lifetime so that the assumptions can be met. In the following, I'd like to talk on the interviews we made. So the first one is about the interviews with wind turbine OEMs. And they said that they would perform a site pre-analysis for a new wind farm to be set up. And they would use initially simulation tools like FastFarm or Flores, knowing that they cause very much computational efforts. And so this is for understanding the situation on this site, but they consider these tools as too laborious and impractical for load analysis and also for certification. And we are a certification body, we can understand that to some extent. And we'll, as Ervin proposed, hopefully have soon other ways to validate those wind farms. Instead, the wind turbine OEMs prefer to have a risk-based approach for certification, as I also described with this approach too. And they even appreciated the certification facilitated by measurements, but only as an option for wind farms to be retrofitted with wind farm control, because they considered that completely a new wind farm to be set up with wind farm control, the investors would not very much like to have a limited validity of the certification for this case, but for a retrofitted wind farm, this could be an option. And the OEMs also said that they would rather prefer verifying the wind farm control features on type level for a type certification already, and prepare the individual wind turbine types for a later use for wind farm control. So and that would be then an amendment option later on, and so to speed up then the design of the actual wind farm. And we were asked about verification of the power curve and about the annual energy production of the wind farm with wind farm control, as power curve verification belongs to type certification of the wind turbine. and if this not could be a new service coming also for from certification. Now jumping over to the perspectives of operators. So the operator said that wind turbine OEMs would only slowly be ready to include wind farm control features in their wind turbines to sell. So they are now implementing what is required for grid code compliance and for requirements they have from for marketing the electricity, but still focus is not very much on functionalities regarding the optimization of loads or of annual power production. That just seems to start. What can be said is that definitely operators will only implement wind farm control if the risk is low or manageable. And what is also important is that the wind turbine OEMs provide an interface between the operator's approach to the wind farm and the actual wind turbine to allow the operator routing of their set points for power, for example. And the operators also said that they don't want to go into details of what and how to dimension these set points, and don't want to take any responsibility for the impact of this routing on the fatigue loads. So it is expected from the wind turbine OEM to provide an interface that allows only influence to some certain extent. And this is, as a consequence, also the expectation to certification, that certification has an eye on this interface and take care that the site-specific conditions won't harm the individual wind turbines with respect to the loads design. The operator said that a retrofitted will only be applied to a wind farm in alignment with the wind turbine OEMs to avoid any warranty conflicts. And the operator said that the functionalities for ancillary services, where also is a lot of talk nowadays about, although they haven't been yet marketed to a larger extent, but they should be implemented already now into the wind farms if they are to be used later on. I want to close with DNV GL's perspectives and also conclude on the interview's feedback. So although it is requested in the interview with wind turbine OEMs, classic certification does not address annual energy production and optimization tasks for certification. So this is something not required or not dealt with in certification. Instead, certification will have an eye on the interface between the wind turbine and the operator, so that there is no harm on the loading. And we are naturally also aware that with wind farm control, the load simulation efforts can increase very much considering all wake effects and failures, as Ervin addressed, and we need to see how we can limit that. Two additional points I would like to raise here is from certification point of view, we think that atmospheric conditions will become very relevant for wind farm control, and that they will be a relevant parameter for site assessments for wind farms with wind farm control. And thus will also be the controllers to be used, and so their design will be specific, and we propose this also for certification to investigate. We are expecting further valuable output from the EU projects FarmConners and Total Control during 2021. But yeah, I'd like to point out that certification is already possible today. So you are very welcome to speak to us in this respect. And I'm looking forward to any questions from you now.
There is a question from Mr. Schlesselmann regarding the atmospheric conditions. What you meant by this?
The atmospheric conditions, stable, unstable, neutral, will have a significant impact on the performance of the wind farm. We'll have to consider shears, wears, negative shears, and that will be decisive on the performance of the wind farm and the expected outcome. And I believe that this should be considered also in the site conditions to analyze as an input to the design of the wind farm, and this should also be reflected then in certification, at least noted.
It should be mentioned that until yet, atmospheric conditions are not required to define for a type certification. We have generic conditions here, and atmospheric layers, stable layers, unsteady shears, etc., are not so far considered in the certification of a rotor nacelle assembly of a machine. But we think, as Nikolai mentioned, that for estimating the wakes, for wake effects, this might become relevant, because we see very different effects depending on weather conditions, on atmospheric layers changes due to specific weather boundary conditions. Is that answered, Reinhard?
Yes, thank you very much. Thank you. It's a very clear answer.
Yeah. Okay. All right. Are there further questions? Maybe directly on the microphone. So if you like to.
Yeah. Hi, this is Wolfgang Moser from RWE.
Hello.
I'd have one question. Are there any activities to bring certification also on an IC level, ICRE maybe?
I mean, the output of Total Control and FarmConners will be public. And so that is information that can be used later on. We from DNV GL plan to have an update of our load standard, and the outcomes of the wind farm control activities will be reflected in that load standard as well. But yeah, let's see when the next IEC revision will show up, and I guess that this will be seen there also in the discussions.
Okay, thank you very much.
Yeah, one amendment to that is that DNV GL is, of course, participating on IEC committees, and we will bring in our experience of wind farm control and certification approaches also in there. Okay, thank you. Then we come to our next presentation. And this is from Vlaho Petrovic. Hello, Vlaho. I see you. He will speak about strategies to provide levelized loading during active power control. The floor is yours.
Thank you, Andreas. I hope you can all see the PowerPoint and you can hear me.
Yes.
Great. So, as Andreas said, I'm Vlaho Petrovic, a senior researcher at ForWind Oldenburg. And today I would like to talk a little bit about how it's possible to reduce the loads or even better levelize the loads in a wind farm, specifically during the time when we are using active power control. For that, I will explain what an active power control is and the control concepts that we have in mind, and also how this influences the power of a wind farm and loads of each of the turbines. Before that, I can start by basically saying a few words about loads, although I'm not sure whether it's still needed, considering we had quite a few talks today about it. But as it was clear in previous talks, loads in a wind farm are obviously influenced a lot by wakes and also by wind farm flow control strategies. Here is just as an example, normalized damage equivalent loads, which we got from our large eddy simulations coupled with aeroelastic code fast, showing how the loads of a downwind turbine change with respect to its position. So we are changing the position of the downwind turbine and analyzing how the loads change, which obviously means that depending on where the turbine is positioned in the wake, the loads should change quite significantly. That's not so new, but what we want to see now is, can we somehow improve, can we somehow reduce those loads by using wind farm control? And yeah, we think that we can. Few words about active power control and what I mean by that. So basically it's about contribution to the power grid stability by adjusting the produced power of a wind farm. So the idea is that the transmission system operator provides a reference, a power reference that a wind farm should track depending on the needs from the power grid. And then the wind farm controller should distribute this power reference to individual turbines in order to really track to produce the needed amount of power. So how to do it? Well, the simplest approach you can imagine is obviously an open loop approach where you say, okay, you get a power reference from the TSO and you simply distribute it among the wind turbines. The simplest approach here would be to say each turbine has to do the same amount of work. So let's say if you have 10 turbines, you simply take the power reference of the wind farm, divide by 10, and send this value to each of your 10 turbines. Obviously, this does not account for for any disturbances, for turbulent wind, for the fact that your turbines might be in wake or not, and so on. So you might have issues following the power reference like that. So logical extension of this would be to close the loop, to basically use the produced power of a wind farm as a feedback. And if this does not correspond to the reference, you adjust the power references sent to the individual turbines. This obviously should work better, but notice here that I still didn't say how to actually distribute the total reference to individual turbines. So how to say which turbine should produce more, which turbine should produce less. And this is actually an additional degree of freedom which we can use in order to control the loads. So this is what we are proposing. Based on turbine loads, you can adjust how much each of the turbines is contributing to the total power production. And what we will analyze in this talk is focusing on tower-based bending moments, and simply saying if one turbine is having higher tower-based bending moments, then it should contribute less to the power production, and vice versa. If the loads are lower, then it should contribute more to the power production. This can be done with a very simple control structure where you simply have a PI controller for each turbine, comparing its loads with the other loads in the wind farm and adjusting the contribution. In order to validate this, we run large eddy simulations in the code Palm, and we used a relatively simple turbine model, but extended with tower loads in order to have an idea how this control concept can actually change the tower loads themselves. First, what I would like to show is the response of the power of a wind farm, where we see how each of the three concepts behave. The blue line showing the open loop approach clearly shows that this does not really achieve very good power tracking because, as I said, it does not take into account wake effects and other disturbances that you might have. On the other hand, two closed loop approaches follow the power reference quite well. And this is, I think, important to emphasize. So both closed loop approaches follow the power reference well, no matter whether we do the load control or not. In fact, it's a side effect, but a nice one. It shows consistently in our simulations that when you try to levelize the loads, you actually get a slightly better power tracking than when you are not trying to do it. Okay. Having seen the power, we can focus on the loads. And now I'm showing the loads of each of the turbine in this 12 turbine wind farm. And what you can see clearly is the wind is coming from the left, so basically from here, propagating downstream. What you can see clearly that normally the downstream turbines have higher loads, which is to be expected. But when you start applying this load levelization, where you say that the downstream turbines should contribute less to the power production and the upstream turbines should contribute more, then you can see that basically the loads shifted from downstream to the upstream turbines. This gets even, this is one thing I want to show. The other thing is when you compare different power reserves. So if you have lower power reserve, meaning that your turbines or wind farm operates closer to the greedy operating condition, obviously the loads increase because your turbines have to do more. Basically, your downwind turbines get more often to their limit, to their available power limit, and then the upwind turbines have to do some extra work. And you can see that in this graph, loads overall increased to a certain degree, but still this load levelization managed to levelize the loads and have a decent, fairer, let's call it like this, distribution of tower loads in a wind farm. So the main point here that I want to make is by using a relatively simple control structure, you can already have a better distribution of loads in a wind farm. This is not where we want to stop with this, so we basically are moving on with this topic. And we are now running detailed aeroelastic simulations coupled with large eddy simulations in order to have a better understanding of loads and possible gains that we can get. But also we transform this control problem into a model predictive control. We think that we got a rather simple formulation there, so it shouldn't be too complex to implement. And since the MPC can work much better with limits that you have in the system, in this case, when certain turbines get to their greedy power production, so basically to their limit available power, we can get even better results regarding the load reduction and load levelization. So the green light, green bars here with respect to the red bars. That's one aspect we are moving further. Another aspect is in terms of lifetime extension, because so far I was saying, okay, when we have active power control, we can levelize the loads. What's even more interesting if you consider the loads over the lifetime, and obviously some turbines will be more loaded than the others. And then during the active power control, now we are experimenting with turbine controllers. You can say to certain turbines, now you can focus more on load reduction and don't contribute too much to the power tracking, and the other turbines take over. And by following this line of thinking, you can again achieve more balanced loading. This depends, of course, on how often you actually have to get to run active power control in a wind farm, but I think it shows some promise for the future, especially as we expect that this mode of operation will be more and more used as the wind energy penetration increases in the power grid. And with this, I would like basically to conclude. If there are any questions about this, I would be happy to answer them, or you can also contact me by email later on.
Yeah, thank you very much, Vlaho. Very interesting. Thank you for this excellent presentation and this interesting results on levelizing those very different loadings on the turbine. So at the end, it would be a big benefit for operation and maintenance costs for a wind farm with this simple strategy. I do not see any questions specifically in the chat. Then I ask in the round if there are any questions to Vlaho on this strategy. You can just open your mic now. Yes, then I would just say for the certification body, it would be then the interesting part if such a strategy has been applied on a wind farm over several years, how to verify the savings that have been done there. Though the indication is clear, there will be savings, but in which amount? So to quantify those savings then on a real project, that would be a challenge then, and as the next step for certification, I think.
Sure. I think that we heard about engineering models that could be used to sort of predict the loading. I think that could be also applied here to show, yeah, what would be a difference with respect without this control.
Yeah, and we had heard about approaches with digital twins and SCADA data that then we might have a nice data set of operation years from SCADA data and could verify with those the real loading at the tower base, at the blade root, or significant points of the wind turbine. Okay, thank you very much. And it's getting late already. In Europe, it's actually almost time to leave the office. So I appreciate that people are still listening here. And I would like to come to our final presentation from Benoit Bichet from ENGIE. Thank you very much that you are here.
Thank you.
And yeah, please introduce yourself and ENGIE, and yeah, feel free to share your screen.
Okay, perfect. Okay, if you can just tell me when you can indeed see my screen.
Not yet, and you're a little, you have to speak up a little bit or
okay,
make your microphone more sensitive.
Okay, I will do that quickly. Is it better now?
Perfect. That's much better.
Okay,
thank you.
Great. And can you see my screen?
Not yet.
Okay.
We see the Zoom meeting participants. Now something. Starting sharing. Yes. Here we are.
Okay, great.
Thank you.
Well, thanks, Andreas. Thank you, everyone, and I would like to thank also Thomas and the crowd here to give me the opportunity to share our conclusions and questions that raised during all the projects that we done in wind farm control. And to introduce myself, I work within the expertise team of ENGIE Green, which is composed of, let's say, 40 people, and we deal with resource assessment, performance analysis, measurements, forecasting, etc. And this year, we worked a lot on assessing the gains of several aerodynamic add-ons as retrofits. And this is why Thomas, that works on the SmartL project, he asked me if I wanted to present some issues that we faced as operators. So here I am. And there is a lot to say, but I have only 10 minutes. But it seems like there is 10 or 20 minutes more after for questions, so I think we have some time. Okay. So as for the contents, the first part will be a very short presentation of ENGIE Green because we are talking about technical topic today, so it's not a place for advertisement. But one thing important is the different maintenance strategies that we have at ENGIE Green. And so I will take 1 or 2 minutes to present that. The next slide will be a listing of the different case studies that we have had the chance to work on at ENGIE Green. And then the 2 other slides, which are the heart of the topic of today, is the return on experience that we have with the wind farm control, and then what we expect as operators for the next years, or maybe for all the discussions that will take place between certification bodies, operators, and ONMs. Okay, so first slide. At ENGIE Green, we are around 500 people with 100 and more wind farms, 1,000 wind turbines. What is interesting is that we have all sorts of manufacturers, of turbine manufacturers. And I already talked about the expertise team. So, and as for the maintenance strategies, what's interesting is that ENGIE Green is actually a gathering of three 3 companies, and this held in 2017. And I listed some bullet points, and I try to categorize a little bit the ways of maintaining our assets. The first one being internalized maintenance, which is quite interesting because, of course, the costs are reduced because the operator is the maintainer as well. But it's based on one unique manufacturer, which is why this 30 people or so team dedicated to maintaining these assets is quite quite close to the machines, quite let's say very they do a very close supervising of the asset, and they know perfectly the turbines, which is really a strength. And what is important as well is that the main components are out of the maintenance contract actually. So again, they have a really close supervising of those main components. For the second category of maintenance, we call it hybrid, and it is, I would say, quite close to full scope, but we have the choice of the maintainer. It is not necessarily the OEM, and the main components again are excluded from the contracts, which can be which is interesting in the long term because you gain more and more experience. And then let's say the classical full scope. So for listing the case studies, I will not necessarily go into details, but I divided this case between R&D and retrofits. The first one being wake steering. So Thomas Duc presented, I guess, some works on the Smart Hull project, but the idea being to deviate the wakes voluntarily. I think we talked about it a lot today, to gain production. And obviously, it's always a trade-off between the loads reduction with the wakes and the gain in production, of course, and the loads that you can expect from voluntarily introducing some static yaw misalignment. Another example is the yaw dynamics. In this case, we tried to modify the parameters of the controller so that we play with the frequency of the yaw motor, as well as the amplitude that can be accepted for that yaw system before it realigns itself. And we took a look at the gain in production, of course, and as well at the yaw activity. And in this case as well, it's a trade-off between the yaw activity and so the loads with the gain in production. The third example is a rain sensor that was installed on a wind farm that faced really strong noise curtailments. The idea being that when it's raining, the sound of the rain obviously covers the sound of the wind turbines. And in this case, you can decurtail or uncurtail the wind farm, which can be, depending on the location, if it's a raining region or not, it can be very very useful to get extra production. And then the last part, I listed some of the subjects we worked on. So spoilers, T-spoilers, vortex for aerodynamic add-ons, but also some tracking system to optimize the yaw. And there are questions to raise about the loads again, but this sounds interesting because it's now suggested or proposed by most of the O&Ms. I'm thinking of Vestas and Gamesa and Ercon, for example. And these case studies were very interesting. And for all those retrofits, we actually installed additional measurement device to try to follow the production, follow the yaw activity, for example. I think we did not spend enough time to assess the loads, for example, spoilers, T-spoilers, or VGs, but we took a lot of time to work on estimating those small gains, because the uncertainties are quite big, as everyone knows, I guess, and it was very interesting to find that it's not easy to conclude, and on top of this, we still need to work on the loads assessment. Okay. For this slide, I tried to list some practical issues that we faced, and basically take a look at what we done and try to see what we could have done better. And so we did not try to give solutions, but rather to ask questions, or to give all the to testify with all the problems that we faced during those projects. And so I tried to categorize this when I asked my colleagues from the operations team what were their concern with the wind farm control projects that we implemented. The first answer was loads, and I guess it's not a surprise. Then it was, can we expect any deviation from the warranty, or when the warranty will stop, what actions can we take? Can we continue? And then, of course, the profitability. But in this case, it's easier, let's say, to prove, or at least to convince the investors that it can be a good opportunity to increase the production of the wind farms. But for the loads, I think it's a little bit redundant with the presentation of Nikolai today, but it was really important. And I'm thinking of the comment that he made on the certification validated by measurement approach. And I think this was really close to what we expect. And it seems like this is also what the O&M expects. So that's interesting. And to try to answer the questions, we have, as Nicolas said too, we have a hard time to assess the loads when we introduce wind farm control. And I listed here some ideas. For example, of course, adding a dedicated load measurement device, and try to use some fatigue loads estimation models. And this, I added here 30 minutes ago, that line in italic, because it seems like a long sim or such software can be really useful, even if it's not certified yet. But this can support our, and let's say our only, yes, I wrote it actually, but it is our only gauge, the experience that we have with the internalized maintenance, more specifically. We have lots of experience, but we cannot turn that into numbers, or say or any certification, and that is a problem, and this is why we want to work on that. And another comment to make for loads is that since we have internalized maintenance or hybrid maintenance contracts, it's very useful to, it's more than useful, it's necessary to be able to assess as much as we can everything that can happen to the main components, because they are out of our contracts. So this is the main. It's really something that we are trying to work on in the recent years. Moving on to our last slide, because I see that the minutes are running, but I think I'm still within time. This is more an opening to a question and answer session, but I try to synthesize a little bit the previous slides. The first question being, how can certification bodies, operators, and OEM work together? So I know it's very redundant, sorry, with the rest of the presentations today, but we see as operators two different topics or ways of having a step forward. And Nikolai told it as well, but sometimes we as developers, we take initiatives of wind farm control because we follow the state of the art in R&D, and we would like to certify sometimes the different outcomes of our projects in wind farm control. And this can be done maybe independently from OEMs, but we have a second case where we actually need OEMs to work along with us so that we can certify maybe certain upgrades, or the last bullet point, I think of the aerodynamics, for example. Sometimes we could certify certain pairs of boundaries versus components, and I will take the example of the aerodynamics. If we decided to play with the parameters of the yaw motor, but we could do that because it was internalized maintenance. Otherwise, I think it would have been complicated. And maybe that the wind turbine manufacturer can tell us, okay, you can play within that range, and this will still be under warranty, or this will still be certified. And that leads us, sorry, to a sort of conclusion that we want to make, or at least a compromise as operators, because the actual situation as for the control boxes is a black box. And generally, OEM suggests a new type of retrofit, and it is either take it or leave it sometimes. And it's hard to really check and understand why these retrofits work well. On the other hand, we would like to have full access to the controller, but we know that it's quite utopic and it will not be possible. So we suggested a sort of compromise, which would be in between white and black, so a gray box. And the idea being to have an interface between the operator and the manufacturer, so that we play with certain parameters, each one having a range of acceptance or boundaries that are defined by OEM. And in this case, the responsibility would be transferred to the operator, and I think that would be a good step forward too. I think I'm finished, more or less. So thank you, everyone. Of course, if you have questions, I will be pleased to answer them. And I left my contact and the one of Thomas too, if you want to discuss all the points that I addressed today. It will be with pleasure.
Yeah, thanks, Benoit. This is Wolfgang from AWE with one question. Can you make an example for boundaries of parameter pair or parameter component pairs that you would like to certify or have certified by the OEM?
I will get back to the previous slides.
I think it's a very smart idea, but I think it's can be very complex, you know, because of the many permutations that may arise from such an idea and the effort that is maybe beyond what an OEM is willing to do. So maybe you have an example.
That's true. I took the example of the yaw control parameters, but in any case, there is a chance that in a few months or in a few years, it will not be necessary to have it, thanks to the power tracking systems. But for example, if there is a manufacturer that which gives an amplitude of -20 to +20 degrees until the yaw system realigns, and some other manufacturers accept only -10, +10. Of course, it depends on the design of the blades, but we played with this range, say, and I think it's quite easy to prove and to assess that the fatigue loads will not be excessive. And I think that, for example, this yaw control parameter, for example, for a wind farm with a very narrow wind rows, it could be useful to have an exceptionally reactive yaw system, or in the other hand, to have something very loose and permissive if the yaw changes very rarely. I don't know if that answers totally your question.
Maybe not totally, but I get the idea. Yeah, thank you.
But it's true that most of the parameters are imbricated, so modifying one makes it a little bit complicated, if that was your point.
Yes, yeah.
Yeah, interesting point from Mr. Moser here on an example, Benoit. I could imagine, for example, that there would be a range of hours operating in your misalignment, giving in advance checked for the turbine resistance, and that this time for experiment would be so open that you have the chance to run a certain portion of lifetime in your misalignment, which has been verified in advance. For example, is another idea would be that, of course, power set points are opened, that there is an interface from the OEM to the operator, that the power set points can be changed. And from our perspective, from the certification body, it is always important that the changes or the requests from the operator, or maybe then also from the grid operator, run through an interface through the turbine controller, that the functionality, the safety system remains active. So there are no bypasses from certain activities, bypassing safety algorithms. So that is one thing. And therefore, from our perspective, there is no way to agree and align this interface with the OEM. You need it to change your operation strategies.
And I have another example in mind, which is curtailment plans. We work iteratively with curtailment plans, especially for noise. For example, we suggest a new curtailment plane that is validated afterwards, sometimes by the OEM, and they give us this validation stamp. For example, yes, you can go beyond this range of or this interval before passing from one mode to another one, and these iterations could take place as well in that interface, even though it's not only a software, but for example, suggesting a new a new set of parameters that would be validated by the manufacturer.
Okay. We are well in time, and we have now some time for some discussions. I see that the number of participants has been reduced to almost 40 from I think we were some more now. But are there any ideas how to bring certification forward from the participants here? What could be thinkable measurements, not to be limiting the innovation, but assuring the innovation and make the innovations in wind farm control acceptable for the industry and the investors to apply? So I ask the round, what you think from your perspective would be a reasonable activity to verify wind farm control activity? Or is it uncritical because we have seen we have savings for the active power control and it is nothing necessary? This could be also a position, the very opposite position maybe.
I have one question I would like to make Andreas Wolfgang again here.
Yeah.
What is maybe most important would be the position of, I don't know, insurance companies or financing institutes when you try to change the wind farm control in one of your assets. Then what about insurance? Even if you are sure that everything will, I don't know, will be fine, loads go down, but in case of any damage, whatever the reason is, what would an insurance company say, and would there be maybe difficulties from that point of view?
Exactly. Yeah.
You don't have any certification.
Yeah. Yeah. And of course, those are very important questions, and those are contractual questions. And that's what ENGIE just mentioned. If there is a range defined for a certain wind turbine type that have been approved for certain variation of operation modes, also including wind farm control modes, then if those ranges are being kept, then the maintenance and the contract and the guarantee remains then active. That's of course the important point. And I think here we have to think about how to convince investors and operators and assurance companies that this is then validated, that this operating window of different modes doesn't change the reliability of the overall turbine and the asset. Okay. Yeah, we will not solve those questions on the contractual issues in between turbine manufacturer, OEM, operator, and assurance companies. What we can do is provide reasonable, good validations based on scientific results. And then at the end, of course, the market will decide. However, what I observed is that there is a big interest in the market as wind power plants become more and more relevant for the electricity market, which is the focus of Work Package 3, how the electricity market needs flexible operation of wind farms, need power reserves, ancillary services, and also reduction of power in case of too much renewable energy power in the grid. And this, of course, is then related to the price level on the electricity market, and therefore it becomes very evident how wind turbines and how wind farms could react on the market demands. And therefore those turbines for the future needs to be prepared for those strategies. I'm pretty sure. I'm very convinced about that. I would say I have no further questions in the chat. We have seen, I think, a wide perspective on wind farm control today. On the scientific side, the simulation side, the potential of reducing loading and saving lifetime with farm control, potential risks with load increases are also shown up. So this is a wide picture we have shown today. I hope you can forward also this information to your colleagues. This workshop is recorded and will be published on the FarmConners YouTube channel. I think we will distribute this mail via LinkedIn. Maybe Gregor can tell something shortly on that.
Yeah, in the meantime, the total control workshop is nearly already there.
All right.
It's just doing the HD version now, and it should be there in not so far from now, and I'll be forwarding that as a FarmConners LinkedIn item, and probably also include that on the definitely also include that on the FarmConners and the Total Control websites, where you can find it. All the presenters, it would be nice to get the slides for further dissemination also on the website.
As PDFs then, please.
As PDFs then, yeah, of course. And other than that, I just got a reflection from one of the participants saying maybe if we actually want to have a more workshop type thing, then next time we could do some breakout groups and organize some breakout rooms.
Discussion.
Which might be a good idea. Yeah.
Yeah.
In order to have a more interactive discussion between peoples. But I think this more presenting style workshop was also a good thing for the time being. And let's keep that up. It's online, so it's relatively easy to do, and we can organize another one if we want to. Maybe one that where we also include insurance companies.
Yes, of course. We don't have them in the FarmConners consortium, unfortunately, and it's hard to get public opinions, of course, from this business. But it would be great, yes, to have feedback, to align somehow the needs. I fully agree. Yes, then I would like to thank you, everyone. Thank you very much for the presenters to have prepared such good presentations with this interesting scientific information and good overview. Join the LinkedIn channel and check the results of FarmConners. We will work on FarmConners the next year, and we will, in work package 2, publish the recommendations for standard and guidelines, and this workshop definitely will contribute on this publication. I thank you very much to the audience for the interesting questions. And then I would like to say goodbye to everyone. See you next time.
Yeah, thank you very much for the preparation. And sorry it couldn't be in Hamburg.
Yeah.
Maybe next
year, maybe in physical.
End of next year, maybe.
Yes, I hope so very much.
Bye-bye.
Bye-bye.
All right, thanks. Bye.
Bye, thank you. Bye, everyone.
Bye.
Bye.